everybody. So, trying to talk about work. Now, work, as you probably know, is force times distance. And if your force is constant, this is this says force is equal to c, a constant, over the interval from A to B, then your work is nothing more than the multiplication of your force times your distance, which is c times b minus a. But it's rarely the case that force is constant. And we are trying to always work towards some kind of Riemann sum. So what we're going to think about is, well, what if your force is changing over this interval? We can take an interval and we can chop it up into smaller bits, and we can get, all right, so let me say the force is different here than it is here. But you can get sort of an average force, intermediate value theorem, and you can apply that and use that force over that distance. And it's going to be approximately equal to the work on the ith interval. And again, we're trying to work towards a Riemann sum. So if we talk about taking the force over the ith interval, and we make sure that our intervals are uniform, then we can apply delta x, and then we're going to have the summation of the force times delta x and the force on that ith interval. We sum that, we apply the limit, and now we have our ability to take the integral. Now, I'm going to skip over a couple of things, and I'll use examples in class. But the big one and the issue that we often face is, how do we describe force? The distance isn't such the challenge. The distance isn't the challenge typically. The difficulty is generating a formula that describes force. So let's begin talking about trying to move something vertically, like straight up. So there are two components in that force component. It would be mass and it would be gravity. Okay, so we need to know what the mass of our item is, and we need to know the gravity component. So mass times gravity and then times distance will give us our work. So it is a common example or a common type of problem where we try and like move water out of a tub of some kind. So we need some kind of generic shaped tub, and we need to be able to determine the volume of that tub. And so what we do is we take like slices, we figure out the area of the slices. So we take the area of the slices, and we generally get a formula for that based on some kind of shape. And then we have the delta y, which is going to take area times the height, and we're generating a volume at that moment. And then we need a density component. That'll talk about how dense that piece is. And then we need our gravity component. Okay, and it's often the case that our gravity component is negative 9.8 meters per second squared. So if we're looking at something where we're trying to move the water out of and into a pipe that's h units above the very bottom of this tub, and it's not a rule, but it's often the case that we put the 0 at the bottom of the tub, and our height h is how far up we go. Then our distance component is going to be h minus y sub k star, where y sub k star is sort of that mid value or the special value. We're able to get the best approximation of the area that we're moving, and we're taking that and we're moving it a distance of h minus y sub k out. So our formula is going to look like this. So we're going to take the limit as the sum of, now here's our area component, and when we multiply it by that piece, we're going to be getting our volume. This is our density component, and this is our gravity component. So here is all of the parts that come together to generate our force component. Here is our distance component. Well, when we apply the limit to that summation, we now get to talk about our integral over the interval from a to b. And our a would be here, and our b would be here. Please note, a would be here, b would be there. All right. Sorry, folks. Allergies are getting to me today. So hopefully that little brief description makes some sense, and we're going to try and apply that tomorrow.